Good afternoon, everyone. Thank you for coming. We're very pleased to have with us today John Stott, a long-term collaborator of some people here at CAR. John got his PhD from Durham University, which was University of Durham at the time.
Yes, they changed it halfway through, actually. So, yeah.
Okay. In 2007, and had postdocs at Liverpool, back at Durham, and was then a Hinser Fellow in Oxford before becoming a lecturer at Lancaster University. John is an expert in observational studies of star-forming galaxies, clusters, quenching, galaxy scale stuff. And today we'll be speaking about anisotropic quenching and discovering galaxy clusters.
Yeah, so I'm going to talk about anisotropic quenching. You can see these papers down here. That's most of what I'll be talking about. So my 2022 paper was a single author paper. I once said there are only two types of people that write a single author paper. I won't tell you what I said about those people. One was genius, and I do not believe I am one. So, then this paper here, I'm sort of, this is a slightly strange word, but I'm sort of touring some things that I didn't get a chance to show off during COVID because I didn't get as many talks done and things then. But yeah, we're talking about anisotropic quenching. So I'll just start with a little overview of galaxy clusters, just so that I know that not everyone in the room works on galaxies or galaxy clusters. And then we'll talk about this anisotropic quenching phenomenon. Then using machine learning to find galaxy clusters in images. And then part 3, if we've got time, probably potentially too many slides, I'll talk about overdensities around distant quasars. Okay, so this is a galaxy cluster. I don't know how anyway. I'll leave it. Right, this is a galaxy cluster. You can see here you've got the galaxies of the cluster are these kind of, we normally call them red galaxies, but this is a JWST image, the first image that JWST released, basically. And so because it's more tuned to the red galaxies you can see here are actually gravitational lenses behind the cluster. And the cluster galaxies themselves are this kind of pale creamy yellow color here. But you can see they've all got the same color, the ones that are in the cluster. You can see some other things there as well. So the cluster galaxies, the gravitational lenses, you may be able to see some spiral galaxies, but mostly the cluster galaxies are elliptical galaxies or S0s. And you can also see stars that are obviously in our galaxy between us and the cluster. So often if you read a galaxy cluster paper, it will say this is the first line. It will say they are the most massive gravitationally bound structures in the universe. And as such, they are excellent laboratories for, and at that point, you then write anything you want. And you see most galaxy cluster papers start like that. They basically consist of hundreds to thousands of galaxies. They have a mass up to, if you look at the very most massive ones, are getting on for 10 to the 16 solar masses, most of that being dark matter. And they have an R200, so basically a radius of up to several megaparsecs. These things are huge, but they're also dense. They're dominated by dark matter. And in fact, you look at the components, sort of 80% dark matter, 14% gas, so that would be X-ray emitting gas. So these things are swamped by X-ray emitting gas. And then only 3% of it is galaxies. But obviously, it's the galaxies that we see with our eyes and our telescopes. And so that's where the name comes from. I don't know if I can remove that at the top there. It's slightly annoying. But the problem is I can't see my cursor. Oh, hang on, there we go. Excellent. Right. That's better. Okay, as I said, they are excellent laboratories for, and in this case, galaxy evolution is what I generally use them for. So they represent a region of space with a knowable dark matter halo mass, containing many galaxies that were likely formed at a similar time and have experienced similar processes. So for that reason, you can test various sort of ideas of galaxy evolution within galaxy clusters or with galaxy clusters. And so cluster environments are likely comparable across all epochs. And you could do things like, say, we have a cluster with a certain halo mass at redshift 1. By redshift 0, this will have a larger halo mass. You can work out what that would be. And you can compare redshift 1 clusters that could be the progenitors of the redshift 0 clusters, compare the galaxies within them, and therefore you can do galaxy evolution studies with them. One of the things they obviously do is, most of the galaxies in the universe are actually star-forming galaxies or spiral galaxies like our Milky Way. But galaxy clusters tend to quench galaxies. And when I mean quench, I mean turn them red, so they're no longer forming new stars because they no longer have access to cold gas to form new stars. This is a plot from Peng from, I think, 2010. You can see on the bottom here, galaxy mass. So very massive galaxies tend to be red, tend to be quenched, don't form any new stars, but also galaxies that are in clusters. So this is local galaxy density here. The most dense regions are up here. So if you're in a very dense region, even if you're low mass, you'll be quenched, and you'll pretty much be quenched at all masses. And if you're a high mass galaxy, you'll be quenched regardless of your environment. And so if you're a high mass galaxy in a cluster, you're definitely quenched. And so environment has an effect on the full range of galaxy masses. And that's an example there of ram pressure stripping, which is something I'll talk about again later. This is a jellyfish galaxy. And I said that the cluster was full of this hot X-ray emitting gas. If you put a galaxy disk, into this at some sort of speed, a few thousand kilometers per second, then as this galaxy hits the X-ray emitting gas of the cluster, it experiences ram pressure stripping. So it experiences a ram pressure here, and that drags cold gas off the galaxy. And that's what this blue light is basically representing. I think it's actually representing new star formation there. But so you're dragging stars off this, and this uses up the gas in the galaxy very quickly, either by compressing it and causing star formation, or causing star formation in its tail, or it can just remove the cold gas without creating new stars. But the point is, it takes this star-forming spiral galaxy and quenches it and turns it into a red sort of passive or S0 galaxy. So that's the effect galaxy clusters have on galaxies themselves. They're also very interesting from a cosmological context. So they represent regions that collapsed soon after the Big Bang. You can look at a kind of cosmic web here from the Millennium simulation. This is just pure dark matter simulation. You can see here that the cosmic web is made of filaments and nodes. And the nodes of the cosmic web, particularly the major nodes of the cosmic web, are where the galaxy clusters lie. So you would expect to find something like this here at this node in the cosmic web. Why is that interesting? It means you can use them to probe cosmology. And so we've got two cosmologies here: lambda CDM, which is the universe we think we live in, where lambda, dark energy, dominates, and an Einstein de Sitter universe where mass dominates. If you first look at this might look a bit strange. These yellow dots are representing where the galaxy clusters are. On the far right there is redshift 0. So an Einstein de Sitter universe is mass dominated, and so you'd expect to see potentially more clusters. But if at earlier times, but if you say we have to match our universe at now, which seems to make sense, so these two universes here match, they've basically got the same number of clusters in them. If we step back in time, the lambda CDM universe predicts more clusters at redshift 1.4 than the Einstein de Sitter universe does, because we're having to match at redshift 0 here. Otherwise, there'd be no point in doing it. And you can see, therefore, you can do cosmology with these things. And basically, if you have a mass function of galaxy clusters and plot that against redshift, you can do cosmology with galaxy clusters. And this is generally orthogonal to things like type 1a supernova and stuff. So you can start to hone down, particularly omega matter. But if you evolve it, you can also do omega lambda as well. Okay. So that was the introduction to galaxy clusters. Now we'll talk about anisotropic quenching. So this was inspired by a webinar at Lancaster in 2021 by Dylan Nelson. He was basically just showing results of the illustrious TNG simulation. And one of those that he showed was a result of Martin Navarro et al. 2021. They found an anisotropic signal in the quenching of galaxies when they looked at 30,000 halos in quite a broad mass range. So from 10 to the 12 to 10 to the 14.5 solar masses. This was at low redshift. The average redshift was 0.08, and it was in SDSS and in illustrious TNG. So they found this anisotropic quenching signal that I'll show you in both the observations in SDSS and the simulation illustrious TNG. This isn't their awful cartoon, this is mine. This was their paper. basically what they're finding is, according to my little cartoon, is that if you have a central galaxy in your halo, I might keep calling this the BCG. That's what it would be in a cluster, a brightest cluster galaxy. But obviously in the 10 to the 12 halo, it would just be the brightest galaxy, the central. Along the major axis of the central galaxy, you have more quenched galaxies than you do along the minor axis. So the minor axis galaxies have a higher fraction of star-forming galaxies represented by these blue circles, or blue ovals, compared to these passive galaxies along the major axis represented by these orange circles. So that's basically what they found. And they call this anisotropic satellite galaxy quenching, but they also, after they wrote the paper, they started sort of also calling it angular conformity as well. So you may hear that too. This wasn't actually the first paper to notice this in terms of the quenching fraction. Basically, another paper in 2016 did this and called it angular segregation. But this paper has mostly been unnoticed in the current discussion. It was a brief part of this paper, and other people had noticed there were more galaxies along the plane of the central galaxy as well before now in clusters. So this isn't a brand new result, but the interpretation that Martin Navarro came up with is certainly new compared to what anyone had done before. This is their signal. So this is quiescent fraction here versus orientation angle about the BCG. So if your BCG has its major axis in this direction, if you sort of go around like that, this is your change in orientation angle compared to the central axis, sorry, the major axis of the BCG. And you can see that things are more quenched along the major axis than they are along the minor axis. The green points are illustrious TNG simulation, and the black points or the gray points are SDSS. So you can see they agree very well with each other. And so they're seeing this in TNG and SDSS. Now, they don't see this in illustrious, not TNG. So there's illustrious TNG and there's illustrious that isn't TNG. The original simulation is just called illustrious. They don't see it in that at all. It's completely flat. And that's because illustrious TNG has a much stronger, well, the reason they think this is because illustrious TNG has a much stronger AGN feedback signal than illustrious. I'll explain that now. So here's my awful cartoon again with some triangles on. So these triangles are representing jets from the supermassive black hole at the center of the central galaxy. Now, on average, you will get your jets coming out along the minor axis of the central galaxy. Things will bounce around in here, even if the actual axis of the black hole isn't lined up with the axis of the galaxy, things tend to leave through the minor axis. So Martin Navarro blamed the AGN in the central galaxy, which sounds a little bit counterintuitive because you look at this diagram, you might think, well, these jets are hitting these galaxies here, they might quench them. So what illustrious TNG is saying, and what their interpretation of that is saying, is that the AGN lowers the density of the intergalactic medium, or the intracluster medium if we're talking about clusters, so the gas in between all of these galaxies, along the minor axis compared to the major axis. And so if there is a lower density of gas here between the galaxies, these blue galaxies here are not experiencing as much ram pressure stripping as the ones along this axis here. They're experiencing more ram pressure stripping. So these are more likely to be quenched than these ones for that reason. Now, it sounds like potentially a slightly strange argument. Potentially, and this is sort of unfashionable and people don't tend to talk about it, but, could this actually be inducing star formation in these galaxies perhaps instead? But that's something that probably needs more investigation, but has generally been ruled out usually, but it's not something that has been investigated so much recently. But this is a stack from illustrious TNG of gas density, and red here means low density, and that is the major axis of the central galaxy. And you can see that the gas is lower density above and below that major axis. And so that kind of lends weight to this argument, and as well as the fact they don't see this in illustrious when they don't have this AGN. Now, a lot of people say the illustrious TNG has very strong AGN in it compared to the other simulations, so maybe that's why this signal is seen, but they're seeing the same signal that they see in SDSS, which is interesting.
Sorry,
is the triggering AGN involved in simulations different? How they trigger AGN?
Sure, to be honest, my understanding is it's a lot stronger in the second in TNG, but I don't know how it's triggered.
Yeah, not know if it's stronger necessarily. It's the way they drive the feedback.
Okay.
So illustrious was bubbles, and TNG was randomly oriented monogens.
So when it's radio mode and the other one's quasar mode. Not necessarily.
I think they're supposed to both move the radio mode.
Oh.
But it's just the way they dump the energy is different. Okay. So I guess this has more of an impact.
Yeah, more directional. Maybe that's it.
So,
Yeah. Yeah. Yeah, well, thanks. Yeah, because I didn't know that myself. Thank you. Yeah, so that's an example of something that looks a bit like this from actual observations. So your central galaxy is here. You can see the orientation is kind of like that. So the major axis is sort of at a bit of an angle here. You've got radio jets coming out from the central supermassive black hole here in red. And then you've got the X-ray emitting gas, the hot X-ray emitting gas in the background in blue. Now these jets are punching holes in that gas and are lowering the density there. And so you can see this in action, this sort of behavior in a galaxy cluster. Now, the eagle-eyed amongst you might notice these things aren't going directly sort of in that direction. This bubble here is not here, and this bubble here is not here. You can see that it does come out along the minor axis, but then it sort of diverts when you hit something or whatever happens within there. So perhaps, on an individual cluster level, you wouldn't see this, but the way it's done is stacked, of course. Now, along the major axis here, you can see that actually this is where the gas is the most dense. So while where the jets are and the bubbles are isn't particularly convincing when you first look at it, you can see that the highest density is along this axis here. So it is still on the major axis. Wrong way. So I thought I'd look for this too. Ram pressure and AGN are the strongest in massive clusters. So rather than looking at 30,000 halos of all masses, I just looked at basically 20 in clusters of 10 to the 14.5 or more solar masses. And this, instead of being at redshift 0, this is at redshift 0.3 to 0.6 from the Clash survey. And to decide whether a galaxy is quenched or not, I just use the median U minus V color, the rest frame U minus V color. So basically the color that crosses the 4,000 angstrom break, and the 4,000 angstrom break basically determines whether or not a galaxy is star forming or not. So the larger that color, the redder that color, the lower the star formation rate or the specific star formation rate of the galaxy. So I looked at the color of the satellite galaxies around the brightest cluster galaxy. Now, this might not look wildly convincing, but what you can see here is these are the galaxies in orange. I've not compressed this just so that you can see also the star-forming galaxies down here. This is color, the 4,000 angstrom break color. These are blue galaxies down here. These are red galaxies up here. But if we look at the average color, you can see there is some sort of sinusoidal pattern there. And once again, the redder galaxies are along the major axis and the bluer galaxies are along the minor axis. This is about a 3 sigma result in terms of the amplitude there of that signal, but it's a free fit in terms of the phase and the wavelength of that signal. Now this was limited because we used HST. We're limited by the HST field of view, so all we could do is look at things within 350 kiloparsecs of the BCG, but we do still see. Not a strong signal, but we do see an anisotropic signal there. If instead of looking at color, we look at quenched fraction, so the number of passive galaxies to the total number of galaxies, you can see that again on the major axis here is this gray region. So these regions are split up into 45, is that right? 45 degrees each. So yeah, 90 degrees either side of these dashed lines here, and so you can see. On the minor axis, you're seeing more star-forming galaxies, and you can see that on the previous plot as well. You're seeing more star-forming galaxies along these minor axes. So it's not quite a sinusoidal signal, probably because we've only got 20 clusters there, but this is the equivalent plot to the plot Martin Navarro had. And to do this, we need a star-forming galaxy color of less than 2. Oops. So anything less than here is we're classing as a star-forming galaxy. So I'm not necessarily wedded to the idea that this is due to AGN. So there are alternative explanations, and I put this sort of kind of infographic in my paper, that if you had, now the clash clusters are pretty spherical, but if you had non-spherical halos, so say the black ellipse here is the BCG, and then you've got the IgM or some other thing coming out here and the same ellipticity as it with the density dropping. If you use a circular aperture, then you will naturally get some sort of sinusoidal signal here, because you've got lower density here than here. So you will get a sinusoidal signal, whether or not there is a real one or not, based on clusters with sort of extreme shapes like this. Now, clusters are generally spherical, and the flash ones are spherical, but it's something to bear in mind. That it might be that. This would automatically make you look like you have this signal. So perhaps the next step would be to use an aperture that was either the same shape as the BCG or the same shape as the halo, if you had information on the halo shape from either the X-ray data or weak lensing. Another explanation is that clusters have a preferential axis of accretion. And so pre-processing of galaxy interactions along this axis may play a part. So if you're the BCG here, it turns out the BCG or the central, its major axis lines up with the tends to almost always line up with the major accretion axis along the cosmic web. And so this is the Millennium simulation here. This is the Millennium simulation with galaxies painted on it. This is a semi-analytic model. And you can almost see with your eyes that the red galaxies here are passive galaxies, the blue galaxies are star forming. You can almost see the anisotropic signal there already. There's a higher fraction of star forming galaxies above and below the central galaxy here than there are along here. So instead, this may be to do with pre-processing. So galaxies in these denser filaments that are coming in this direction rather than this direction, they've had interactions and been quenched already before they get to the cluster, or more of them have been quenched before they get to the cluster. And so this might be the explanation for the signal instead. And so the next step compared to this would be to use wider field imaging of the clusters, which is what I'll show you in a minute, because we've got a paper hopefully being written on this at the moment by my PhD student. There was a third anisotropic quenching paper that came out. This was Ando et al. 2023. And so they also see this signal. They weirdly don't see it at redshift 0. There's a bit of a mess there. So they don't agree with Martin Navarro. Strangely, they don't see it. But they do see it at sort of moderate redshifts, the same as we do. So that's kind of strange. So yeah, they go up to redshift 1, and this is using hyper-SU prime cam Subaru data. And so they get the strongest signal at intermediate redshifts. What they do, they check though, is one of the things I was worried about is the shape of the halo and therefore local galaxy density. You know, is the local galaxy density just denser? You know, it's just higher along the major axis of the BCG. So they do check that in their paper. And so this is local galaxy density along the bottom here for different redshift ranges. And if you pick sort of one of these redshift ranges here, you can see that along the minor axis, along the major axis, they're still more quenched than the minor axis, so these red and blue points, even at the same local density. So there's more quenching still going on. That doesn't necessarily rule out, it might rule out halo shape, but it doesn't necessarily rule out pre-processing, because the pre-processing, they may have been in those more major filaments for longer than they've been in anything coming at the minor axis angle. They also looked at stellar mass. They didn't find a correlation between quenching and stellar mass, which kind of goes against the ram pressure stripping argument, because it's easier to quench low mass galaxies than it is to quench high mass galaxies. So maybe they don't see this as their mass cut is already quite high. They have a mass cut of about 10 to the 10 solar masses. So this is a paper by my PhD student, Harry. So Stevenson in prep. We have looked at Subaru data as well, and we see a very strong signal. There's Harry. I've replaced the picture I usually use of him because he hates it and he likes this one instead. So enjoy his picture. This here is the signal we now see with Subaru. This is Subaru Subprime Cam. So this is the signal we now see with that, and you see it's a very strong signal. This is at 2 times R200 for a stack of clusters. You see a very strong signal at 2 times R200. Now, you're thinking 2 times R200 sounds like a long way out from the middle of a galaxy cluster. And so it's starting to sound sort of unlikely that this would be anything to do with AGN, unless you've got bubbles rising through the medium or something. But even so, it seems unlikely at 2 times R200. We did this in basically within radii and also in annular bins. So here, this is the amplitude of the sinusoidal fit to the anisotropic quenching here. But this is everything within the radius. So this is within fractions of R200. That peaks at around 2 R200. And then this one is within annuli. And again, that peaks within about 1.5 to 2 R200, I guess, because it's not accounted for everything in between it. And you can see then the universe returns sort of back to normal again at about 3 times R200, which is good because at some point it should return back to being isotropic, of course. And so, yeah, so within about 2 R200, you're seeing this isotropic signal. And I believe that probably means this isn't related to AGN and potentially instead related to the halo or related to the major axis of accretion. We also looked at the surface density and find the exact same thing that Ando find. So we find that along the major axis, I asked Harry for a plot and he sent me this. So I apologize for that I apologize for that x-axis. That's not my x-axis. But anyway, imagine surface density is going up in this direction. You can see that things are still more quenched at the same surface density of galaxies along the major axis than they are along the minor axis. And so we're in agreement with Ando. So I'm not saying this means that I think it probably means it's not the halo shape, but I don't think it means it's not pre-processing because, as I say, things could be living in those filaments for a long time before they get there, particularly in the major filaments. So there might be more quenching going on in there, more quenching processes. Oops. Some further thoughts. So cluster crossing times, sort of a few gigayears. So this must be relatively quick for this to change. So it probably is something like ground pressure stripping. I know the result from Ando showed there was no dependence on stellar mass, but it needs to be something that happens on a scale of about a gigayear. It'd be interesting to know, obviously, we don't know what's happening here, so it'd be good to look at simulations instead. You know, is this just for galaxies falling in for the first time, or is there some form of rejuvenation happening? You know, could it be the case that you can rejuvenate galaxies with the jets? Is it seen in other cosmological or cluster-specific simulations, you know, other than Illustris TNG versus Illustris? And there are many we could check for that as well. And then if you do an AGN and a non-AGN run, can you replicate what's happened in Illustris versus TNG as well? So that is basically, sorry, the summary of part 1. So we're seeing this across a range of halo masses and redshifts. Still don't know the underlying cause. It's most likely to be pre-processing, I believe, rather than AGN. And you can find out information in these papers here. Has anyone got any questions on that before I go on to the next? Oh, yeah, go for it.
So, wouldn't it be ideal to show or rule out the AGN as a reason, looking at if it's possible, like with LOFAR, if you don't see any previous activity from AGN, because for instance, it's like you said, unlikely. If it's a giant radio galaxy matching the size of the cluster,
yeah,
then you may say, oh, it might be possible. So whether you see anything in those clusters that you work on and say we don't see any AGN activity or previous AGN activity, especially with LOFAR, that would be possible.
Yeah, so there's two things there. Exactly what you're saying. Either use LOFAR, because LOFAR, so I can't remember now exactly, so I'm certainly not an expert on LOFAR, but there's a way of using LOFAR to trace old radio cavities. And you can also look in the X-rays and see X-ray cavities, of course. And I don't think, to my knowledge, anyone's ever gone out and correlated X-ray cavities with the galaxy population in those X-ray cavities. They may have done, I'm not sure, but I've not seen a paper on that. And so for more nearby galaxy clusters, there's probably about 30 galaxy clusters where you could probably do this with, probably within redshift 0.1, you could potentially try and look at whether the galaxy population looks any different. So my idea is you would basically compare radial distance from the center of the cluster to distance from an X-ray cavity or to local X-ray density, for example, or the presence of a radio jet. If there is a jet, you can still see.
Yeah.
Yeah, and see whether that that
It's
does.
always there. It's not. It's,
Yeah. So I suppose the jet has some lifetime, so you might want to.
That's why I said with a
Yeah.
produce activity.
Yeah, yeah. And I think LOFAR can tell you that, can't it? Yeah. So I think that's, you know, a more detailed next step to do. We wanted to just, first of all, just do it with a large imaging survey, just a wide field imaging survey, sorry, just to see what the radial dependency of radial dependence was. I think I've seen that, but yeah, I think it's worth checking exactly that. Yeah. Anything else? Yeah.
I like AGN jets, but I thought the model was quite unconvincing. I have
Yeah,
to say,
yeah.
on various counts.
Yeah, I'm not here to defend it.
So I mean, how you set it up in cosmological simulations, that is, I think, still quite a bit from reality.
Yeah.
If you look for large scale jets that you need, that must be a long-term active jet. So actually, the phase in the galaxy is less than 1 million years. So you're looking for 10 to 7-year active jets, where how you orient that in the galaxy shouldn't be that important. I would expect that it's quite random how the black holes oriented.
Yeah, definitely.
To the major axis. The black hole spin where you expect the jet direction. And if you look at the bubbles, and they are structures that live for a few million years, or maybe 10 million years. I don't know if that's enough to influence the star formation history of the galaxy in that way.
Yeah.
Causes such observations.
I guess if you have bubbles, they're always going along the same direction, perhaps. You know, you always get, if the AGN is always going along the same direction, it's possible. On it, maybe it's an average thing, you know, averaging over lots of halos, you tend to see this. But yeah, I'm not convinced either. Yeah, I'm not here to defend it.
Not from bubble observations and X-rays that they do not go in the same direction.
Yeah. Yeah. But how often are they along the major axis? Maybe that's, you know, potentially something to look at. Maybe it's just an absence of things along the major axis.
Can probably argue that we don't have.
Yeah, exactly. So it could be that, or, you know, anyway, I'm not, I always find myself defending this other person's paper in these talks. I think, why am I doing that? But yeah, but I'd like to know the real reason. I think it's probably pre-processing, but I would like to know the real reason. Shall I crack on with next bit? Yep. So using machine learning to find galaxy clusters. So we've looked at things going on in galaxy clusters, but I thought since there's a lot of machine learning going on here, this is searching for galaxy clusters with deep learning. This was with my PhD student, Matthew Chan, who wrote 3 papers on this sort of stuff and then sadly went to industry. He is now doing, I believe he's doing machine learning for a wedding planning company, if you can imagine that. So anyone here interested in breaking out of astronomy or machine learning can, the sky's the limit. Okay, so this is an example of the algorithm. That there is a galaxy cluster, and you can see that it's predicted there is a galaxy cluster there. So clusters were originally selected by people like George A. Bell and my favorite astronomer, Fritz Zwicky, by eyeballing monochrome photographic plates like this one. This was the Mount Wilson Observatory making these photographic plates, and you can look through here and find overdensities of galaxies. Oh, no, sorry, that was Palomar, sorry. Nowadays, they're conventionally selected using X-ray emission or the Sunyaev-Zeldovich effect. So the X-ray emission just comes from the hot X-ray emitting gas in the cluster. The Sunyaev-Zeldovich effect is the effect of that gas on the cosmic microwave background as it passes through that and scatters the photons. And then also looking at a red sequence. So this is a color magnitude diagram. Are you seeing lots of red galaxies? And therefore you might be seeing the red sequence of a galaxy cluster. However, X-ray and SZ generally produce candidates that are then eyeballed by astronomers at optical wavelengths in order to confirm the presence of a cluster. So this is what I've done many a time with the XMM cluster survey. And so we see something like this, then we look at an SDSS image or whatever that is, and go, yeah, that looks like a galaxy cluster. Sometimes instead that's a giant spiral galaxy nearby or something like that, or it's a set of AGN altogether or something, just along the line of sight. But yeah, we're looking for extended X-ray sources that correspond to some galaxies. So I thought, if you have to eyeball the candidates anyway, why not just look for clusters and images using artificial intelligence? So we kind of recreate the work of Abel and Zwicky, but using computer vision techniques instead. And so this is not classifying known photometric sources or detecting galaxies and then deciding whether they're in a cluster or not. It is instead looking at the sky to see if it looks like a cluster. So it's not, I believe, is this one of your papers, Jim? Is this, yeah, so it's not looking at a galaxy already and then saying, what is it? It's looking at the sky. So we look at a region of sky here and go, that looks like a cluster. We look at a region of sky here and goes, that looks like a field. So we just look at the whole sky, break it up and look at different bits of it. So yeah, this was Matthew Chan. Obviously, he's graduated. We use this Deep C, which was deep learning for galaxy cluster extraction and evaluation. It's based on the faster RCNN algorithm by Wren. And RCNN is a region-based convolutional neural network. So it finds things in images and then classifies them. So instead of deciding whether your image is of a cat, it might look at a whole field full of cats and dogs and find out where all the cats are, for example, or in our case, clusters in space. This is the architecture of it. So you feed it an RGB image. It looks for features within that, creates a feature map, has a region proposal network, and then it then looks for objects to detect within that. And then it finds you a galaxy cluster. In a nod to George A. Bell, we extracted the RAN deck coordinates of the A. Bell galaxy clusters, which were identified in Wen's SDSS catalog of all the clusters in SDSS. And we selected clusters between redshift 0.1 and 0.2, so quite easy to see, with at least 20 members inside their R200. And we use GRI filters to make RGB images. Okay, so can I get this to work? So I'll play this now. This is the algorithm looking for galaxy clusters. So you can see one there, right? Try and see if you can see the next one. Okay, what do you think it is? Do you think it's that one? I think it's that one. Yes, so there you go. So this is the algorithm. This is a GIF of the algorithm finding galaxy clusters. All right, it's got surely there. Well, maybe there. Okay, yeah, both of them. I did this somewhere else that would remain nameless. And one of the professors was very proudly saying how he was quicker than this. And I said, it's a GIF. This is just like, this is for audience participation. This isn't the algorithm running live in PowerPoint. So he was very proud of himself until I explained that to him. Surely down there somewhere. Yes, right. I've not practiced.
It doesn't have redshift, it's just the image.
It just has the image. It says no other information. It's a color image, so it understands that things have color and redshift, but it may understand that, but it doesn't have. So it does not give in redshifts. Not this particular algorithm. We did experiment with other algorithms using catalog data instead. So it provides a location and a confidence score. So that is 92% chance of being a cluster, for example. We then tested it on unseen clusters, less than redshift 0.2 on a region of the sky we'd not looked at from RedMapper, so these weren't ABO clusters. And with a 70% confidence threshold, we gave the best F1 score performance, so the best performance in precision and recall. So you're trying to be near the top of this corner here. And that was the sort of best performance we got with it. And we didn't tweak it any further. We could have done, but this was just purely a proof of concept. We were getting a recall of 87% and a precision of 77%. So it was very, very successful and did very well. But yeah, we haven't. The plan would be, in fact, I may now say this. Yeah, run this on the Subaru Hyper Prime Cam SSP data, which I've not done. We probably should. And in the future, maybe run it on LSST data. Maybe even try and get it in somewhere towards the end of the pipeline of LSST for the UK version of the data access center. But it could also rapidly confirm candidates discovered in current and forthcoming X-ray and SZ surveys. So you could just do the thing I showed before, sort of doing a galaxy cluster zoo, as it were, and just show the location on the sky in SDSS or LSST, etc., and get it to confirm whether there's a cluster there without need for human interaction. We did some further machine learning papers. We did a paper on using k-nearest neighbors to estimate the redshift of clusters. This is pretty successful. So this is the actual redshift, and this is the predicted redshift. I actually only found out afterwards that the predicted redshift we used was the photometric redshift, and so there's an intrinsic scatter here anyway. But basically we're seeing a very successful correlation here. This takes all galaxies within a fixed radius of a known cluster center and compares the photometry with a training set without telling it anything about anything, without telling it anything about galaxy evolution, etc. So it's basically a redshift encode that doesn't, it sort of learns essentially SED fitting itself, as it were. We did it specific to clusters, as all galaxies in that region are assessed at once, basically. And it achieves a very nice score there, delta Z over 1 plus Z of 0.01 with unseen clusters from SDSS in the redshift range 0.05 to 0.6. And then finally, Matthew was also keen to look at richness of clusters because, we've found the clusters, we've got their redshift. Now it'd be great to find out what their mass was. So if we can use optical data to get their richness and imply their mass from that as well. And so he also created a multi-stage ML algorithm called auto-enrichness to distinguish between clusters and line of sight galaxies to obtain more robust richness estimates as well. So the summary of part 2. So 5 minutes, deep sea demonstrates that novel computer vision techniques can be used as a successful alternative to conventional candidate selection. And then Z sequence and auto-enrichness can get you a photometric redshift and potentially a cluster mass as well. And I'd be interested to run this on LSST potentially. And that's the original deep sea paper there. So finally, quickly, I'll just talk about overdensities around quasars. I won't go too much into this, but we want to find distant galaxy clusters because they give you the best constraints on galaxy evolution and cosmology because you've got this longer baseline in time, basically. There are various reasons why it's hard to find galaxies that are distant. X-ray surveys have a flux limit. SZ surveys require a mature ICM as well as X-ray surveys. There may not be a mature intercluster medium at higher redshift. And also SZ surveys get confused with submillimeter galaxies as well and star-forming galaxies once you get up to these redshifts. And optical surveys require a mature red sequence, generally. People have looked for high Z clusters around and protoclusters around radio galaxies, but quasars aren't usually used. And Jim's looked at this and found quasars in kind of 10 to the 12.5 solar mass groups, and Ryan Hickox has done something similar as well. So we use QSAGE, which is our quasar sightline and galaxy evolution data. This is basically to do quasar sightline searches, but we also use it now to look for quasar clusters, basically. So I'll just skip through all that, but you can see here we've got lots of galaxies at the exact same redshift as the clusters in this survey. So this QSAGE survey, is a redshift survey. So we're getting very accurate redshifts there. We're finding lots of galaxies at the same redshift as the quasars themselves. This is at redshift 1 to 2, basically. The average redshift is 1.5. So we're looking at overdense systems at around about redshift 1.5 and finding all of these overdensities. And in fact, 8 of our quasars out of 12 are overdense, which does sound strange. If you think about Jim's result there, that they would tend to be in lower mass halos. Why are these appearing to be in high mass halos? And if you look at the images here, you can see that there's the quasar there in the diamond, and then all of these squares and circles around it are other galaxies other than the quasar at the same redshift. And this is within a field of view of about 1.3 times 1.3 megaparsecs. So these are quite dense structures at these redshifts. So we're definitely tracing something. If you stack them all together, again, you can see this high density of things at the same redshift as the quasars. So there's obviously, something there that's sticking out around these quasars. We can estimate the masses from a spherical collapse model and find that these would have masses of sort of 14.5-ish or so if all of the mass in that area collapses down into the same halo. And some of them may already be in the same halo, of course. I would argue that this thing may well be some sort of virialized system, for example, with there's so many galaxies there within such a small radius. But this doesn't make sense. As say, Jim and Ryan Hickox had already found that these were generally in lower mass halos. But when you look at the higher luminosity quasars in statistical clustering studies, you find that the higher luminosity ones tend to be in slightly higher mass halos, so 10 to the 13 solar mass halos instead. Apparently, this is not the case at redshift 3, so we're at redshift 1.5, where even the highest luminosity quasars seem to avoid overdensities, and Traynor and Steidel have done some work on this. But at redshift 1.5, they don't seem to be avoiding, they seem to be in them. So why are our quasars particularly in these very overdense regions? And it's because the Q-SAGE quasars are actually for quasar sightline studies. So the idea is you want a bright quasar that can shine through galaxies along the line of sight, so you can get a really nice UV spectrum from it. Really nice UV spectrum requires a bright quasar. So these are basically the 12 brightest quasars at redshift 1.5. We know that Eddington luminosity correlates with black hole mass. Black hole mass correlates with galaxy mass. Galaxies in clusters are more massive, so the most luminous quasars probably should be in overdensities. And this is where Q-SAGE sits in the absolute magnitude, B-band absolute magnitude there. That's where Q-SAGE sits. So all of these quasars are at the very extreme end of the absolute magnitude distribution. And so this kind of makes sense from a Silk and Reese kind of argument. You know, if feedback regulated growth of black holes is correct, the UV brightest quasars should live in the most massive halos. So the mass of the black hole correlates with the mass of the halo to the 5/3. So the Eddington luminosity should as well. It is seen in cosmological simulations such as Booth and Shea and McAlpine 2017 in Eagle. And so it looks like we are seeing this for the just most extreme quasars, the brightest quasars. And perhaps we might go and follow up these quasars soon with to see if there are any passive galaxies there as well. Go and look for red sequences, etc., in these potential overdensities around these quasars. Okay, I will leave all that there. So I've talked to you about three things: anisotropic quenching, machine learning to find galaxy clusters, and then the fact that you can find high redshift galaxy clusters if you look at the most UV luminous quasars. If anyone here is interested in ultra cool dwarfs as well, I've also found some of those in Q-SAGE, and I can show you some of those later if you like. So yeah, thank you very much.
Thank you, John. Any further questions?
Nice talk. Thanks for the site.
That's right.
You showed in the first part of the talk, you showed the illustrious plot was the distribution of the gas density.
Yeah. That one?
Yeah. Has anyone tried doing that for the data? If you take something like Planck map and stacking it, taking out the orientation of the galaxy.
To my knowledge, that has not been done. No, it might be something that's
Yeah. To trace.
Is the resolution good enough? I suppose for lower redshift things.
Planck is 5 minutes or so.
Okay, yeah. She did it right, redshift 0.05 or something. Yeah, that'd be interesting. Yeah.
So if you have, do you have presumably your result, you've already got the angle.
Yeah.
So
Yeah, that's a good idea. Yeah. Something to look at, definitely.
I don't. I thought on the cluster finding stuff with the machine.
Yeah.
Is it? I mean, all of those clusters that appeared in the GIF appear to have very kind of similar kind of angular size. Is that just the way the plot was made, or is there?
It's sort of by design because we're all at basically the same redshift.
Yeah.
So, yeah, sorry, Gary, I'm sort of predicting what your question is going to be. But
so does it indicate that it's good at finding clusters in particular redshift ranges and not others?
Well, we've not tried it. I suspect the answer is that we probably want to train it across a range of redshifts, and maybe even potentially have 2 or 3 versions of it or something, or have a way of augmenting it such that it knows when things are at different redshifts. But yeah, it is currently it's just a proof of concept, and it was basically set to a specific small redshift range for nearby. It's basically redshift 0.15 essentially.
And are those clusters that you see, I mean, when you draw a box around them, yeah, they're really obvious. I mean, are they things that you would have picked out when you read sequence stuff anyway, or are these things?
I suspect so, because these are, so we, so it doesn't see a catalog, of course, it just sees an RGB image, but we fed it the Abel clusters from a catalog that was based on a nearest neighbors algorithm, not ours, it was Wen's 2012 catalog. And then we then tested it on a region that Wen didn't use from data it hadn't seen. But that instead was on Red Mapper, which maps the red sequence. So Wen is a nearest neighbors, Red Mapper is just red sequence. You could argue these are similar, particularly for low redshift clusters. And so yeah, there may well be the fact that, you know, if you wanted to look at weird clusters or something, or, you know, things at higher redshift, you'd probably want to train it, you know, because at redshift 1.5 or so, for example, if you had good data, you're going to have far more star-forming galaxies in there as well. You may have a more compact core and then star-forming galaxies around. So it may not be, these are probably not applicable at high redshift, but perhaps you could train it on the things that you might see at high redshift.
That's a significant part of the problem, right?
Yeah. I'd be curious to know what happens if you train it on things that were selected in X-rays, see what it finds, train it on things that were selected in SZ, train it on things that were selected in Red Mapper, whatever it is, and then see whether or not these are different populations.
One more question?
I'm not trying to connect the radio, it's just because I looked at some quasars show very few different radio morphology, FR15.
Yes.
And obviously, the one way to look at the environment, when we look at normal galaxies or radio galaxies, I see no radio detection. So I was wondering, I struggle to estimate the density or under or over density for the quasars that I was working on. It was not possible somehow. So did you see any differences in the radio morphology that I was wondering, or did you have a look at it in detail?
Didn't look at the morphology. I just looked at the ones that were selected in radio and not selected in radio to see if there was a difference. We didn't see a difference between those. Of course, doesn't mean it was switched on or not when we were looking at it, of course, but we didn't see a difference. But I didn't look at the morphology of the radio. So, I mean, very low numbers, so I guess it might be hard to do. Yeah.
Okay, that's our done, exactly. So let's thank them.
Thanks.
I actually had a couple of questions.
Oh, yeah, sure.
So this was the thing about the AGN explanation.
Yeah.
It seems to make sense to me is it seems to neglect the azimuthal component of the orbits of these satellites.
Yes.
I mean, they wouldn't necessarily be hanging out along the minor axis for the whole interval, right? They would be
It's one thing I'm quite interested to know is, I don't know the answer to this. Looking at like organic bias simulation, where they hydrangea, you know, where I think it's embedded in a. We got a leap, by the way. Where I think it's embedded in a larger cosmological simulation, and they do a sort of re-simulation within it. So I think it does.
there are some like that.
Or Bahamas. Maybe I mean Bahamas.
Yeah.
What I'd be interested to know is if I come in along a major axis, a major filament, how long does it take before I'm sort of randomly in that cluster, you know, sort of randomly virialized in there, or am I always sort of orbiting like that? So these galaxies ever see these ones? I'd be interested in, you know, when do they do them?
I think that's probably a lot of what it is. If you come in along the filament, you stay in that plane.
Yeah,
You
there's no
stay in the
reason
higher
for you
density region as you've described.
Yeah.
Whereas if you're coming in somewhere else, either you're more radial in your orbit anyway, or you're just undergoing a mixture of different environments. That could be it.
So it could be that. I mean, yeah, as you say, I mean, I don't know much about this sort of orbital mechanics of it, but I presume it's quite hard for you to then get out of this.
Yes, once you're in the plane.
I mean, I suppose you might can't sort of like that or like that, but even so, whereas these things that come in now, the density thing is interesting, that there's no even for the same local density, you still get the difference. And I think that maybe things have been in larger filamentary structure for longer, or have experienced, you know, more extreme environments than sort of more minor filamentary structure in this direction.
I think that makes sense. That pre-processing component, like you said, is important. Another test I thought you could do, you mentioned how you could run something like an astro split without AG.
Yeah.
Something you could also do, which would be a lot quicker, is you could run a semi-analytic with or without non-pressure stripping.
Yeah,
Because if that's supposed to be the dominant,
You can see.
you could turn that off. Yes.
Yeah,
There are versions of SAMs run on Millennium that also take account of stripping outside of the halo, so elementary pre-processing.
oh, that's not even something I thought of, yeah.
Yeah, so I wonder if you could run that with RAM pressure off to see
what
if you lose the signal.
Yeah.
or something like that. And that
Yeah.
can be done more quickly.
Yeah. Yeah,
If you're interested in that, let me know.
Yeah,
It's
that sounds really
exciting. I'll ask them with that big processing component.
Yes. no, that sounds really interesting, Rob. Yeah,
Cool, yeah.
and you even saw, with that very presumably,
Yeah.
relatively basic SAM that was on the picture that I showed, it was probably Bauer 2006. or
Okay,
whatever it is.
good old days.
Yeah, I think so. And yet, by eye, you could almost see the signal in
Yeah,
that.
you could see it, which is another argument for why it's probably not AGN, because we do have AGN in SAMs, but it doesn't change the density of the gas.
Yeah, and I
It
wouldn't
just
have
changes
thought
the
the
average.
Bauer 2006, I wouldn't have thought was as sophisticated to make lower density either side of the.
No, it definitely doesn't do that. Even now, we're not modifying the density for variants
Yeah.
in CGM. So that would have been RAM pressure stripping effect, I
Yeah.
think, rather than, so
Yeah.
it'd be interesting to see.
No, it'd be really interesting. Yeah, I've got no time. I've got to do all this stuff while obviously you're starting teaching, haven't you? So,
Yeah,
exactly.
Yeah,
Same situation.
very busy, but a student one day can do this.
Yes.
If you're interested, I can put you in touch, and the run on the SAM is much quicker, of course, so